let's talk about lesson 8.4. I'm gonna skip the do now. Skip the do now. Let's talk about electrical energy. If you kind of think back to lesson, rather unit 7, we talked about electric energy briefly, so we can consider electrical energy work. Work can be considered electrical energy, right? Now, okay. And really, these are the formulas for electrical energy, right? And you can see that on your reference table. You can also see that on your reference table, W is equal to work, right? Work is electrical energy. And now we're going to talk about power, right? So power is the rate at which work is done, right? P is equal to W over T. And electrical power is really just the rate at which electrical energy is done, right? Rate at which electrical energy is transferred. And we're going to measure power in watts again. Right? So we're going to measure power in watts again. And these are all the formulas for power. That includes voltage and resistance, right? Now, I'm sure most of you guys have phones, right? Most. And if you ever tried charging your phone, right? If you guys ever tried charging your phone, then you'd realize that, well, my charger gets hot or my phone gets hot. Or if I use my phone for a long time and I use it for really intensively, it also gets hot. But why is that? Why does electricity, why does charging, why does doing anything involving electricity get something heated? Why does it heat it up? That's because as electricity, again, we learned it from last topic, 8.3. As electricity goes through a wire, you're losing a lot of that energy due to heat because electrons are kind of bumping into these atoms. Right? These atoms are getting in the way, and these electrons are bumping into the atoms, they're colliding. And through that collisions, you generate friction, and that friction generates heat. So as you run electricity, you lose a lot of energy to heat. Take, for example, a gasoline car. Gasoline car. Right? And so a lot of the energy comes from combustion, from the combustion of the gas. But 20% of the energy that you gain from doing that only goes to moving that car. You lose 70% of the other energy due to heat, right? Because all the heat you're using, all your loss to heat. And so while you might think you're getting 100% of power here, using 100% of your energy, you're really only getting a partial amount of it in a car. Same thing happens with a phone, right? The outlet might give you a lot of energy, but as that energy goes through the wire and goes into your phone, you're losing some of that energy due to heat. So really, while 100% of energy might be coming out of the outlet, your phone only charges up to 80%. And so you lost 20% of that energy due to heat, due to heat. And really, at that point there, I'm not sure what energy loss you have though, by the way. I'm just making up these numbers just kind of make it relatable, right? And let's take a look at the left image, an electric car. In an electric car, 100% of that energy, most of it does go to moving the wheels, right? 90% of it does go to moving the wheels, whereas you lose 10% of that energy due to other things like heat, right? So you definitely lose a lot of energy here due to other stuff, right? So definitely makes a huge difference. Makes a huge difference. And so now really let's just go to solving problems. Right, so how much energy is expended when a current of 5 amperes is in 5 ohm resistor for 5 seconds? Let's just do this first practice problem with you guys, just so that we can see, so that I can guide you guys. So our current is 5 amperes. My resistance is 5 ohms, and again, I can write ohms as omega. And my time is 5 seconds. and we're looking for work. We want to know, well, how much energy is expended? And again, we're going to look back at our reference and say, well, which formula, right? Which formula has I, R, T, and W? Well, if I look at my reference table, we see that the only form that it consists of I, R, and W is W is equal to I squared RT. So I is going to be 5 squared, 5, T is also 5, and then we get 625 joules. Now let's say you don't remember the unit for work, right? Because again, alternatively, you could just do this. The unit for I is A. Since we're doing I squared, we do ampere squared. The unit for R is ohms. So I can just write ohms. And the unit for time is seconds. I can just write seconds. So alternatively, the unit for work can be A squared times ohms times seconds. So in the case that you actually forget the unit for joules, you have this alternative unit you can turn to, which I will still mark correct. 2B is asking you, is doing the same thing, right? So they're saying resistance of 2.9 ohms, right? And you have a voltage of 1.5 volts. And what is the rate at which electrical energy is transformed? What is the rate? When you see that rate of energy, well, they're looking for power, electric power, not work. They're looking for electric power. And so the only formula that has P, V, and R is P is equal to V squared over R. And so B, C, and D are really the same type of questions, right? So you guys can do that yourself. But let's take a look at this. To increase the brightness of a desk lamp, the student replaces a 50-watt incandescent light bulb with a 100-watt incandescent light bulb. Compared to the 50-watt light bulb, the 100-watt light bulb has what? Just some little information here. Pretty much every outlet in households, regular American households, they provide a voltage of 120 volts. Some European countries provide a voltage of 110 volts, but the standard American voltage is 120 volts, and that's the voltage the outlet provides. The power. So let's take a look at power, right? So we're doing power here, and really, if we take it, we're kind of comparing resistance and current. So really, R and I. If we take a look at the formula that contains power and I, right? Because we see here that we have my power, or we have two powers here, and so my power here doubles. The formula that contains power and current is P is equal to V over I. So my voltage here, they're connected to the same outlet, my voltage is going to be constant. And so really just based on this formula, we can say that, well, P and I are directly proportional, right? There's a linear relationship there, which means that if I double my power here, then I also must be doubling my current, which means I am getting more current, more electric current. So by that mere fact alone, we can really just eliminate two of these choices already. Think about it another way. If you increase your power, you're also increasing the rate at which electrons flow, right? So really, your electric current has to increase. It has to. On the other hand, if we compare R and I, right? And again, we learned about it in 8.2. If I increase my electric current, that means I'm decreasing my resistance to that electric current, right? Logically, that has to make sense, right? They are inversely proportional, right? If I increase the amount of electrons that go through a wire, that means my resistance to electron flow has to decrease. They are inversely proportional. And really, your answer here is less resistance and more current. All right. I'm gonna end on that. The answer is there. Oh yeah, 2F. Regardless of the method used to generate electrical energy, the amount of energy provided by the source is always greater than the amount of electrical energy produced. Explain why there's a difference between the amount of energy provided by the source and the amount of electrical energy produced. Again, the reasoning goes back to the carding, right? Some of your energy is lost as heat. Like, for example, charging your phone. Your phone does not get all the energy from the outlet. A lot of it is lost as heat, which is why your charger gets hot. All right,